Hello, my name is Fabian Schwarz and I'm a PhD candidate at the CISPA Helmholtz Center. I'm going to present joint work with my supervisor Christian Rossow to you, which is about SENG, the SGX-Enforcing network gateway, authorizing communication from shielded clients. The question we are tackling in this project is, what are the origins of corporate network communication and how can gateway firewalls use this information for fine-grained traffic control? We are looking at a typical corporate network environment where client workstations and servers are segmented into disjoint internal subnetworks that are interconnected via a central network gateway. The gateway firewall centrally governs all network accesses and enforces network policies based on the connection IP addresses and port information. For instance, it might allow connections to the mail server or a subset of the intranet or internet respectively. However, when internal clients become compromised by an attacker, these traditional network policies are too coarse-grained to prevent data exfiltration and command and control channels. To resolve this problem, the firewall must be able to distinguish between malicious and benign sender applications for tight traffic control. Therefore, our goal is to shift from traditional IP and port-based firewall policies to per-application policies to prevent unauthorized communication. However, the problem is, secure traffic to application attribution is a challenging task because user and system malware have several opportunities to evade and subvert traffic attribution attempts. First, malware can defeat port and heuristic-based approaches by using traffic morphing techniques to hide in benign network communication. Second, malware can inject itself into allow-listed processes to abuse their trusted identities for firewall bypass. For instance, if malware injects into a trusted browser, all malicious network communication will be wrongly attributed to the browser process and thereby evade the firewall. Third, malware can perform a system-level exploit to completely subvert host sensors and spoof application identifiers. The bottom line is that current approaches fall short of providing secure per-application policies because they fail to protect trusted applications and their traffic against system-level attackers, and they do not base their traffic attribution on precise, unforgeable application identifiers. In a nutshell, we face the following threat model. We assume the existence of on-path network attackers and allow the corporate client systems to be fully compromised by system-level attackers. On the client side, we only trust the user and the client hardware and follow the classical Intel SGX threat model in that we exclude denial of service, side channel and physical attacks. The central gateway is assumed to be fully trusted and we are thus staying in line with the common bastion host assumption. For brevity, we also treat all corporate server subnetworks as trusted. To enable secure traffic attribution in this challenging setting, we propose SENG, an SGX-enforcing gateway service coupled with a client-side runtime. SENG's client-side runtime shields applications in Intel SGX enclaves and securely tunnels their network traffic till the perimeter firewall. The gateway-located SENG server cooperates with the client runtime to expose secure, hardware-rooted application identifiers to the perimeter firewall and ultimately enables the central enforcement of secure per-application policies. To allow for easy deployment, SENG does not require any modifications to client applications and is compatible with existing firewall and gateway services. So, given an application on a compromised client system, the first question we have to answer is, how does SENG shield client applications and their network connections against system-level attackers? What SENG does is, it takes an unmodified client application and executes it inside an SGX enclave using an SGX library operating system. In our implementation, we use Graphene SGX, which supports dynamic loading of unmodified Linux applications and provides common POSIX abstractions and a file system shield. However, Graphene SGX relies on the untrusted host network stack and is therefore insufficient to shield the application connections and DNS traffic. To fill this gap, SENG integrates the SENG runtime for shielding the client network traffic. The SENG runtime exposes a trusted socket and DNS API and includes the Lightweight LWIP TCP/IP network stack. The network stack manages all network communication of the application securely inside the SGX enclave. For protecting the application traffic in transit against system and network attackers, the SENG runtime includes a secure tunnel module. The tunnel module protects all trusted IP packets via DTLS and therefore enables secure IP-level tunneling of application traffic. To summarize, we have seen how SENG shields client applications and their network traffic using Graphene SGX and the SENG runtime. Next, we concentrate on the question how SENG performs the central traffic to application attribution. Looking at our corporate network environment, the SENG server runs at the central network gateway and listens for tunnel connections by shielded client applications. Each SENG runtime automatically establishes an attested DTLS tunnel to the SENG server using a fresh RSA key pair. For the attestation, the runtime binds an SGX attestation report to the RSA public key and ships it via the client certificate. The SENG server then verifies that it communicates with a valid enclave and looks up the shielded application identity in the trusted allow list using the enclave measurement. Note that given the trusted TCP/IP stack of the SENG runtime, each tunnel packet carries a trusted inner IP packet. Therefore, the SENG server can assign a unique enclave IP to each shielded application to expose the application identity to the gateway firewall. After authentication, the SENG server can attribute all network communication from and to the attested tunnel directly to the shielded application, and given that shielded traffic arrives only through attested tunnels, the firewall can easily block any unauthorized communication. Note that SENG also supports external shielded applications, but we have to skip the details due to the given time constraints. Given that we have seen how SENG shields client applications and exposes their secure application identifiers to the gateway, we can now turn to the question how SENG ultimately defines and enforces per application firewall policies. What the SENG server does is, it uses the trusted enclave IP addresses to override the source addresses in firewall rules. Network administrators can define application-specific IP subnetworks, for example a trusted browser subnetwork, and the SENG server will then assign IPs from this pool only to the specific shielded browser applications defined by the administrator. The gateway firewalls then just have to be adapted to work on the fine-grained application subnetworks instead of the coarse-grained host subnetworks, which makes the approach fully compatible with existing firewalls. So, for example, given a rule for web communication to external servers which allows data exfiltration potentially, SENG can enforce that only trusted Firefox applications can reach out to the internet. In the same way, SENG can also be used to restrict access only to hardened applications, for instance a Postgres client with TLS mode enabled. Or considering incoming connections, SENG can restrict access from external client to an internal FTP server only to a specific FileZilla version. So putting the policy enforcement in a nutshell, the gateway firewall enforces SENG's per application policies on traffic from and to the application-specific IP subnetworks. To summarize, we have shown how SENG enables secure per application policies while staying compatible with existing client applications and gateway firewalls. Before concluding the talk, we can now have a brief look at the performance impact of SENG. For our performance measurements, we have implemented a prototype of SENG and evaluated it on a set of network benchmarks and real-world applications. We have used a local setup with 1 gigabit network cards and compared the performance of SENG against native Linux and vanilla Graphene SGX with exitless E and O calls. Regarding the downlink throughput of a single TCP connection using IPv3, native Linux and Graphene SGX reached an average of about 930 megabit per second. SENG showed an overhead of about 3 to 7%, reaching about 870 megabit per second, which we regard as practically feasible for client workstations. We also had a look at the HTTP download performance using curl, which showed a slightly higher overhead of about 9 to 14% for SENG, but we still regard it as feasible in practice. We also evaluated SENG's performance for server applications by measuring the response latency and throughput of NGINX. In this case, native execution drastically outperformed Graphene SGX and SENG, which both only reach about 15K requests per second. That means about 37.5% of native performance. This was not surprising, however, and was on par with observations by the authors of Graphene SGX and is caused by the missing support of asynchronous and batch system calls. To overcome this bottleneck, we implemented an alternative SENG runtime, which we call SENG SDK and which is based on the Intel SGX SDK. SENG SDK does not use a LibOS and significantly outperformed Graphene SGX and the SENG runtime by reaching about 90% of native performance. The results have shown that SENG can benefit from performance improvements of the underlying primitives. Further evaluation results about the SENG runtime and SENG server can be found in our paper. To summarize, we have discussed the challenges that had to be overcome to enable reliable and secure traffic to application attribution. We have proposed SENG as a possible solution which routes the application protection and identifies untrusted hardware and ultimately allows to enforce central per-application firewall policies. Last but not least, we had a look at the performances of our SENG prototypes for client and server applications, which showed promising results for practical usage. Note that all prototypes of SENG are available as open source projects on GitHub. Finally, I want to thank you for your attention and would be happy to answer any additional questions.